Hello all, in this video we will see how we can convert a context-free language into a context-free grammar. So as you all know, context-free language and context-free grammar are languages and grammars respectively accepted by a push-down automata. So context-free grammar is the grammar accepted by a push-down automata, and context-free language is the language of a push-down automata. And now the conversion context-free language to context-free grammar. It's actually there is actually no algorithm for this. There are no rules of thumb or anything like that. It is actually more of an art than a science. That is, as and when you practice more, you will be able to write it better. That's it. So we will see how we can do this. So as I told, there are no algorithms or no rules at all. So we have to just see how does it work. Okay. So we will see some context-free languages and we will convert that into context-free grammar. I repeat, context-free languages and context-free grammars are languages and grammar of push-down automata. So the first context-free language that we will take is L is equal to A raised to N, B raised to N, or an N greater than or equal to 0. So N can be 0 or N can be greater than 0 or equal to 0. See, what we need to understand here is that it means that we need to understand the meaning of the language or understand the speciality of the strings in the language. Here it is A raised to N, B raised to N. That essentially means that there are equal number of A's and equal number of B's. So in every alternative that has an A, we should ensure that the alternative has a B also. See, when you have a prediction like this, for example, S gives AS or BS, something like this, this means that you are free to take any prediction, any alternative to expand us. You can keep on taking S gives AS, S gives AS, S gives AS, and you can end up deriving lots of A's. So that is like this, S gives AS. Now this A can be, I'll use derivation trees instead so that you can easily understand. Yeah. So for example, S gives AS. Now you can choose this S to expand that to AS again. Now AS again, now AS again, and you can keep on doing this so that at the end you may even give some epsilon and substitute this epsilon. So you are getting a string just with A's. So in order for this not to happen, because when you have loads of alternatives on the right hand side of a prediction, you are free to choose anything. The user is free to choose anything. So you can't ensure that the number of A's and B's are same. So in order to ensure that, what you need to do is every alternative should contain equal number of A's and B's. So when the user takes lots of alternatives, whatever be the alternative that the user is taking, he or she will end up with equal number of A's and B's. We have to design the right hand side like that. If you are designing it like this, it will not work, because the user can simply take these alternatives repeatedly and end up with lots of B's with no A's at all. So this is not, this is not allowed. So what you can do is, you can write, so the A's come first, isn't it? So A, then something can come in between and it should end with B, isn't it? This string is actually starting with A's and ending with B's. So starting with A's and ending with B's. Okay. Now, a more number of A's and B's can come in between. And the string can even be empty, because n is greater than or equal to 0. When n is equal to 0, you don't need to have anything at all. So n can even be equal to 0. So I say that this is sufficient for the grammar. Don't worry if you're not getting it, because it's actually a matter of practice. We will see how we can derive some random strings A, B, B. Now A, B. Now string will be derived for sure. A, B, B, B. All these strings can be derived, it will work definitely. So S is A, S, B. Now S is A, S, B. See, S is always allowing A on left hand side and B on its right hand side. So we will not get mixed A's and B's mixed up. Now we are deriving this. So I need just 2 A's and 2 B's. So I am substituting this S with epsilon. So I am getting A, epsilon BB, that is AABB. So this has been obtained. Now S gives to get AB, ASB. Now I just need one A and one B. So I am substituting this S with epsilon. So S is AB. So AB has been obtained. Now S gives A, S, B. I need 3 A's and 3 B's. So A, S, B. I need one more A and B, S, B. Now since I got 3 A's and 3 B's, I can stop. So the output is A, epsilon, B. So I got this also. So our grammar is working perfectly. So this is how we write this. Okay. So that's it. We will move on to the next exam. So our next example is L is equal to A raised to N, B raised to N, C raised to N. Okay. Here N and M can be greater than or equal to 0. It can be anything. Okay. So A raised to N, B raised to N, C raised to M. See, A raised to N, B raised to N. It has already been designed. It is this thing. So A raised to N, B raised to N. It's actually concatenation. So we can easily approach this in this way. So A raised to N, B raised to N has already been done here. We already know the grammar for that. So or this is a simpler version. So we can call it A and we can call this B. Okay. So we will write a grammar grammar for A and B and will concatenate it. For example, S gives the grammar for A concatenated with the grammar for B, isn't it? Now the grammar for A, you know that it is this thing, A, B or epsilon. Now you have to write the grammar for B. That is, you have to write down the grammar for C raised to N, C raised to some M. Okay, M greater than or equal to 0. So this is one question that we need to do. Okay, see, C raised to M, that means yeah, I'll use the same. So C raised to M, that means any number of C's can be derived. So you can simply write it as C derives C or epsilon. That is C derives CC, the C again derives CC, the C again derives CC, and it goes on. For example, C derives CC. Now this C can again derive CC. The C can again derive C. And when you are done with it, you can stop the process by substituting epsilon. So please to understand that on the right hand side of a string, when you finally derive a string, the string should contain only terminals. No non-terminals are allowed. So if you have any non-terminal, you have to substitute that with epsilon to avoid that. Because when we discussed regular grammars, I have told you that on the right hand side you can for a string at the end of derivation, it should contain only terminals. No non-terminals are allowed. So if you are having a non-terminal of epsilon as part of the production, you can get rid of it by substituting epsilon. Okay. So any number of C's can be derived using this expression we have seen that. So we can write down for B, you know that it is CB. So any number of C's can be derived by this. Okay, that is CB. Now this B can be again derived by CB. This B can again be derived by CB, and it goes on. So you can get any number of C's by this expression. So if you are combining this, you can get any string. For example, initially null string, that is because M, N, everything can be empty. So empty string can be obtained by substituting S with AB. Now A with epsilon and B with epsilon. Now you will get empty string. So that is accepted. Now A, C, C. Okay. So no, A, B, C. That's a allowed string. So S gives AB. Now A is actually AAB. I just need one A and one B. So I am substituting this A by epsilon. Now this B can be substituted by CB. Now I need 3 C's. So B is substituted by CB again. This B is substituted by CB again. And I need just 3 C's. So I am substituting epsilon to get rid of this B. Now read the leaf notes from left to right. So A, B, C. This is what exactly what we need. So this grammar is working perfectly. So this is how we do this. So we will move on to the next example. So the next example that we are seeing is L is equal to A raised to N, B raised to N, C raised to M, D raised to M, where N and M are greater than or equal to 0. See, please to note that for any string a PDA cannot accept. You can neither write a CFL or nor write a CFG. Okay. For example, A raised to N, B raised to N, C raised to N, D raised to N. A PDA cannot accept that string, so you cannot you cannot write a grammar for that too. Yeah. So yeah, that this is a string. So you know that A raised to N, B raised to N. You know it. How you can do this? A raised to N, B raised to N. So we can take it as A. C raised to M, D raised to M. You know how you can do this. So we can take it as B. So it is actually A concatenated with B. So S is equal to A concatenated with B. And you know that for A, what do you need is A raised to N, B raised to N. So A, B, we are really familiar with that, or epsilon. Now for B, you know that it is C, B, D or epsilon. You are familiar with this also. So when you concatenate this, you will always get the correct answer. For example, A, B, C, D. A raised to N, B raised to N, C raised to M, D raised to M. Let's check how we can get this. I am simply writing a random string. S gives A, B. Now A is giving you A, B. I need two A's and two B's. So I am expanding it once more. A, B. Now I am done because I just need two A's and two B's. Now I just need one C and one D. So I'll write C, B, D. Just need one C and one D. So I am stopping it. So when you read the leaf notes from left to right, A, B, C, D. Yeah, exactly this. So our grammar is working perfectly. So we will see the next example. So the next question is W raised to R. L is equal to W raised to R. See, W raised to R is actually a palindrome. For example, if W is AB, W raised to R is the reverse form of it. So BA. So it's actually a palindrome. So when you are given languages like this, it will be difficult for you to understand how you can write the grammar. So what you need to do is you should understand the meaning of W raised to R. W raised to R means it's actually palindromes. So in case of palindromes, you know that the starting character and ending character should be the same. So S gives either, if it is starting with A, if W is defined over A comma B the whole star. So if it is starting with A, this should end with A also. ASA. If it is starting with B, it should end with B. Then epsilon can also be part of it to get rid of this S. So that is the only condition we have. That is in a palindrome, the condition is the starting symbol will be the ending symbol. The second character should be equal to the second last character. We'll check whether how we can create the palindrome A, B, A. Now the reverse form is A, B, A, isn't it? A, B, A, A, B, A. We will check how we can do that. So I'm starting with S. So the first and last characters are A. So I'm using this alternative A, S, A. The second character and second last characters are B. So I'm using the second alternative B, S, B. The third and third last characters are A. So I'm using the alternative A, S, A. So I got 6 characters and this is all in the string. So I'm using epsilon to get rid of this S. So read see A, B, A. So that is the string. This is actually W raised to R. That means the string and its reverse form is definitely even length because 2 times the string, that is definitely even length. So we will see about odd length palindromes also. So for that it will be L is equal to W, C, W raised to R. For example, this is a format wherein W element of A and B, A's and B's. So in this case, what do you need is S gives ASA because definitely if the starting string must be the ending string also. If it is starting with B, it should end with B. Now to get rid of the S, you can use C instead of epsilon, because epsilon has been applied in the very middle, right? So you can use C instead. For example, if it is ABA, CABA, you can substitute this S by C. So you'll get ABA, CABA. That is, the middle character is not epsilon. It is the middle S is not substituted by epsilon, but it is substituted by C. That's it. So we will see more examples now. Next, you know that you can simulate balanced parentheses using PDA. We have seen that in the PDA design, balanced parentheses. So we will write down the context-free grammar for balanced parentheses. So you know that it should be first the opening bracket, then anything can come in between, and it should be closing bracket. So anything that is starting with an opening bracket should also end with a closing bracket. And again you can have parentheses like this, that is starting brackets followed by ending bracket, another starting bracket followed by an ending bracket. That means the parentheses always need not be nested parentheses. So to simulate that, you can write SS. That means any number of this opening and closing can come close together. Now to get rid of the S at the end, you can use an epsilon. So let's see how it is working. So we will take a few sample examples and check whether how does it work. So yeah, this is the first example, this is the second example, next in parenthesis, then this is our third example. Now anything that starts with a closing bracket is not allowed. It will not be generated by the grammar. All the negative strings will not be accepted by the grammar. Okay, we cannot write that. For example, this will not be accepted by the grammar. We will check this first. Closing bracket. Now alternative starts with a closing bracket, so we can't derive this. Now we will check with this. S gives opening bracket, S closing bracket. S can be substituted with epsilon. So opening bracket and closing bracket. Got this. Now S opening bracket, S closing bracket. Now again opening bracket, S closing bracket. Now again opening bracket, S closing bracket. So you got this. Now you can substitute this as epsilon. So 3 opening brackets and 3 closing brackets. So you got this. Now an opening bracket, opening bracket, S closing bracket. Now an opening bracket and closing bracket. So opening bracket, S closing bracket. See, if you are substituting this S with epsilon, to get this you can't derive it anymore, because the derivation will stop here, as we don't have any more x to expand. So what do you need here is, you need 2 such brackets here, isn't it? So you derive S to SS. Now this S can be derived as opening bracket, S closing bracket. This S can be derived as opening bracket, S closing bracket. Now what happens is, you can replace this by epsilon. You can also replace this by epsilon. So opening bracket, closing bracket, opening bracket, closing bracket, closing bracket. Exactly like this. So this prediction can be used to create any number of repeating S. Any number of repeating opening and closings like this. Okay, so it is working. So we will move on to the next example. Oh, sorry. Excuse. Yeah. So we'll go to the next example. So next example is L is equal to A raised to N, B raised to M, A raised to N. Yeah. N comma M can be greater than or equal to 0. If, you know that a PDA can be designed for this, because all the A's can be pushed and all the B's can be ignored, and when the A's come you can pop the A's off of the stack. So a PDA can be designed for this. So we can definitely write a context free grammar also. Let's give it a try. So S gives ASA. Because if B is absent, you need a string just made up of A's alone. So that can be done. Now if you have lots of B's at one point, you can write it like that, A, B, A. Now to stop the derivation of S, you can substitute epsilon. Now any number of B's that doesn't depend upon A's number of A's can be derived. So for that we can use the string for B raised, the grammar for B raised to M, which is BB or epsilon. Now let's check whether it is working or not. See, for ASA, this is to get equal number of A's and B's. Now A, B, A is used to start the derivation of B. So what we will do is, we will first generate as many A's as we require, and once that is done, we will go to the derivation of B's. Because once we choose this alternative, we cannot generate any more A's. So first we have to be done with generation of A's, and then only you can start the derivation of B's. So for example, we will take the string A, B, B, A. Let's check. So S gives, initially I want to generate all the A's as I told. So A, S, A. Now S gives, I need 2 A's and 2 A raised to and B raised to M. Sorry, it's B's. Sorry. All these are B's because no, it's A itself. So A. Oh, I made this difference here. So it's actually A, B, A. Yeah, exactly. No. So equal number of A's. So A, and any number of B's. So 3 B's. So this is what I want to derive. Yeah. So ASA. So 2 A's and 2 A's. Yes, so 4 A's. I have generated all the A's. Now I can start generating B's. A, B, A. Now when you expand B, I need 3 B's. So BB. Now again BB. Now I need one more BB. Now we want to get rid of this B by substituting it to epsilon. So A. Oh, sorry. See, there is a mistake because when I am using this alternative for the third time, I am getting A's also. So I don't want to do that. So first time I used ASA to derive 2 A's, and second time I am using A, B, A to derive this second pair of A's. Because this alternative for B already contains A's. So BA, now I can write BB, BB. See, this is not the only way in which you can write down the grammar. You can write it in many different ways. For example, another alternative would be ASA, B. Now, yeah, ASA, B or BB or epsilon. For example, we will see that too. For example, S gives the same string ASA. Now ASA. Now S can be replaced by BB. B can be replaced by BB. So AA, BB, AA. So the same string. Yeah. So for a same question, same grammar, same question, you can have different answers, and all of them would be correct too. Yeah. Now the grammar for L is equal to 0 plus 1 the whole star. Yeah. So that is any combination of zeros and ones are allowed. So the grammar is very simple. S gives 0s, 1s or epsilon. That is, you take 0 or you take 1, you take anything and keep on expanding this. That is, for example, if you want the string 10, 10, 11, S gives 1s because it's starting string is 1. Then S gives 0s because next character is 0. 1s because next is 1. 0s because next is 0. then 1s because next is 1, 1s because next is 1, and end up with epsilon. So you'll get 1 0 1 0 1 1. Yeah, that's it. So this is how you do this. Now if it is like the languages like 0 plus 1 the whole star 0 1, what if it is like this? Let's see we know how to design it for 0 1 the whole star, so we will call it A, we will call this B, and we will call this C. Yeah, or we can call this B together because 0 and 1, this is a single thing. So S gives for 0 1 the whole star, it is 0s or 1s, plus we have to write that it is S gives AB. See, S need not be the start symbol, you can choose anything. S gives AB, and for A you know that it is 0A or 1A or epsilon, and for B you know that it is 0 1 itself. So you can do this. For example, 1 0 0 1, this is from this first part and this is from the second part. Let's see how it is happening. S gives AB, now A is 1A, now A is 0A, now A is epsilon, and B is 0 1. So 1 0 0 1. So you can get that. So this is how we do this. We create strings of this particular format. So we will see another example. Yeah, L is equal to 0 1 1 plus 1 the whole star dot 0 plus 1 the whole star. So we will see how we can derive a context free grammar for this particular language. See, 0 1 1 plus 1 the whole star. Okay, so you can choose this alternative or this, similar to this. So you can call this A and you can call this B to make this things easy. So S gives AB. Now yeah, A is actually you can have any combination of 0 1 1 or you can have any combination of 1A, isn't it? So 0 1 1A or 1A or epsilon. See, instead of the 0A and 1A, it is 0 1 1A because these three things has to come together always, and 1A or epsilon. Yeah, that's it. So this is for this particular part. Now for B it is 0 plus 1 the whole star. So 0B or 1B or epsilon. So this will do. Let's take an example is actually 0 1 1 0, isn't it? 0 1 1 from this and 0 from this. Let's see. S gives AB. Now A is 0 1 1 A. I am substituting epsilon for A. B is 0B. So I am substituting epsilon for B. Yeah, 0 1 1 0. So this is how you can get this. Okay. So we will see another question, that is L is a string containing equal number of A's and B's. Equal number of A's and B's. Here we don't have any pattern. So A's can come first, but there should be equal. B is also in that. Now B's can come first, but there should be A is also in that. We should make sure that A also come along with B to make sure that their number is equal. Then epsilon. See, you may be thinking that why I am not writing ASB or BSA or epsilon. The reason is that if I am writing ASB or BSA or epsilon, what happens is then it becomes mandatory that the string that start with B should end with A. That will become mandatory. That is why I am writing it like this. Okay. So because I need to include both A and B together in all the alternatives, then only their number will become balanced. Then only I can ensure that their number has become balanced. For example, we will check the string B A B. So let's see how does it happen. So S gives B S A S. So so I got this B, I got this A. Now I need one more AB. So we'll see how we can do that. So I'm substituting epsilon with this because I just need two more characters. So for this is I'm using as bs. I'm substituting with epsilon here, I'm substituting with epsilon here, so it is b a b. Yeah, same thing. So we can generate this. So hope that is clear. That is in some cases you will need the trial and error strategy to get the grammar that really works. So that's it. Hope you understood. Thank you.